the next chapter about non-volatile memories that we have and can use in the ATmega. A non-volatile memory is a memory that retains its data even after a reset or power cycle. For instance, the program that we upload to the ATmega in the exercises remains there even after the power is disconnected. Apart from the program memory, which uses flash technology like the USB thumb drives, the ATmega is also equipped with a small EEPROM, which is perfect for instance, configuration data. In this chapter, we first have a look at the flash. Apart from the program, we can also store in and retrieve data from it. In the second half of this chapter, we will talk about the EEPROM. Let's get started. The laptops, PCs and smartphones that we use on a daily basis are following the von-Neumann architecture. In this type of architecture, programs and data are stored in the same memory, such as the RAM. It simplifies the architecture and compiler design, but on the other hand, opens up the opportunity for some interesting attack vectors, as we discussed in one of the earlier chapters. The AVR architecture is fundamentally different from the von-Neumann one. It uses two separate storages, one for the program and one for the data. The ATmega 328P is based on the Harvard architecture. The advantage is that different kind of memory technologies can be used. For instance, for the data, the ATmega uses SRAM, which is volatile, while the program is stored in the non-volatile flash memory. Apart from that, the address space for the SRAM also includes the I/O and registers. On the other hand, a small portion of the flash is reserved for the bootloader, which allows us to use UART to program the flash memory. Internally, the 32 kilobyte of the ATmega 328P is organized in 16-bit sized words accessible through 16,384 addresses. And further, depending on the ATmega that we have, in several pages. For instance, the flash of the ATmega 328P used in the Arduino consists of 256 pages, each consisting of 64 words. Remember, one word is 16 bits or 2 bytes in size. This is important to know, since if data is stored in the flash, the entire page is to be rewritten. Hence, the flash is not byte or word writable. Unfortunately, the flash survives only 10,000 write cycles in average, which is probably not enough when a program misuses the flash as a temporary storage for variable values. But for programming, it is sufficient. Let's say you program the flash through debugging, etc. 25 times a day. That means in average, you can expect the ATmega to last for a year. That is, if you do not have any breaks or weekends in between. The beautiful part of the flash is that it is in-system programmable. That means a program can program the flash. In fact, that is exactly what happens if the bootloader writes the data sent through the USB and UART to the ATmega. Also, and that is even more practical, large read-only data blocks can be stored in the flash as well. In the chapter about interrupts, we already facilitated this functionality to store the sound data in the flash, since it is read-only anyway and would not have fit into the SRAM at all. the function program read byte then reads the data from the array, here the first element. This function expects the address of the element to be loaded. And all elements were stored in the array sound_data_data. Please note that the keyword const, such as this one and this one, does not determine if a variable is stored in the flash or in the SRAM. It only tells the compiler that there is no writing access to the variable, so it makes it easier for the compiler to apply certain optimizations. In addition, it ensures that the software developer does not alter the value even by accident, since any write access to a constant will abort the compilation with an error message. Instead, what makes the array to be stored in the flash is the macro procmem that is added between the type definition and the initialization values. Since the values cannot be altered, it is also marked as constant. So how do we get some data into the flash so it does not occupy the small 2 kilobyte SRAM? First, define the data like in this example. To extract the data, simply an index to the array is used. As a first change, mark the array as a constant and add procmem from program space, which is to be included. The issue is that array with index 3 points to a location in SRAM. However, the data is no longer stored there. So we have to get the address of the element at the index within the array and give that address as a function parameter to program read byte, which is aware that the data is located in the flash and loads it from the appropriate address. Besides from loading bytes only, there are more functions available, such as word, which is 16-bit, or dword, which is 32-bit. But we can also store floating point values and pointers in the flash. Instead of writing, for instance, char, procmem, and then the variable name, we can just use proc_char as type for convenience. But this is not true for an array of pointers. The way to store constants in the flash instead of the limited SRAM is nice. However, if it comes to strings, there is a pitfall which prevents the shifting of the string content to the flash. It will remain in the SRAM instead. Here is an example. We would like to store those 5 strings into the flash. Right now, all of those strings will remain in the SRAM, even if there is no write access to the array. After compilation, we will see that 56 bytes are stored in the SRAM. To list what is stored in the data section, we use the object dump with avr. We see that apart from the strings from here onwards, also the pointers to the strings are stored. For instance, this is S, T, R, I, N, G, and these are the pointers to the strings. We must not forget that strings are always terminated by the null terminator, which is for instance here. And here it begins again with STRING. I, N, and so on, terminated by a null terminator. According to the previous examples, an assertion of const and procmem should shift the values to the program space. However, storing string arrays in a program space is not straightforward. First, we need two const keywords. The first one defines the pointer string table as immutable. That means that its value, which is the address it points to, cannot be changed. However, we also have to make sure that the content cannot be changed. In this case, the content is an array of addresses to strings, hence the second const. By now, the variable string tables is an immutable pointer to an immutable array of pointers. Let's see if that worked. Compiling the program and displaying the data section in the RAM reveals that it did not work as intended. Let's have a look what is in the data section. We see that the strings are still in SRAM, but the pointers which were in front of them originally are not there anymore. It seems we shifted only the pointers to the flash memory. But why is that so? The procmem attribute applies only to the declaration it is attached to. Here, that is the variable string table and what is stored in that array. And stored in that array are not the actual strings, but pointers to the strings. Hence, while the array of pointers is stored in the flash, the strings are not. That did not go well and was probably not intended. Since the attribute only applies to the declaration, to store the actual strings in the flash, we have to make a little diversion and declare all strings to be stored in the program space. Then an array is defined full of pointers to the program space, which in turn is also in the program space. The type of the pointer in the program space is pgm_p, which is the same as constant pointer to a character. Let's see if we have been successful, and it looks like we were. The data section is empty by now, and the object dump also confirms it. The entire array of strings is in the program memory by now. If you are interested to play around with the program, I copied it to the directory course memory flash and then read data from flash in the VirtualBox image. I also attached it to the resources folder on the right. After storing the strings into the program space, the question is, how do we access them by now? In this example, we take the address of a particular entry in our string table. Given that address, to program read word returns a pointer to the program space. Then we use the helper function string copy _p, which accepts a destination address in the data space, here buffer, and a reading pointer in the program space. After this copy function, the data will be available in the array buffer, and it can be sent to an LCD to be displayed, for example. Apart from string copy _p, there are a lot of helper functions available in the AVR library. I'm attaching a link to a list of those functions to the resources folder for your convenience. When you search for program in the internet, you will come across forum entries about alternatives to program. What are those alternatives? I just would like to lose a few words about another method instead of program. Instead of program, it is possible to use the non-standard keyword double underscore and flash. In case that the flash keyword is not supported, the software developer should provide a fallback method to program. The functionality in the if and the else branches is exactly the same. The implementations are just different. Personally, I always worked with the proc-mem path, and I have no bad experiences with it, but in the end, it is just about preference. Why do we even have to go through the complexity of determining the storage location of data? Well, C is made for von Neumann architectures, in which all data and programs are stored in one memory. But in Harvard, we have two memories, and C was not designed to support those cases. For instance, as you can see, the addresses can be the same, but point to two different memories. Therefore, it is up to the software developer to tell the compiler in which physical memory it will find the data. So far, we have only talked about how to read constants from the program memory. But can we also write to this memory? Writing to the flash, which is also the program memory for the ATmega, during program execution is a delicate process. First of all, the flash is organized in pages. If data of, for instance, 1 byte is to be written to the flash, the entire page needs to be erased first. The size of the page depends on the ATmega you are using. For instance, the size for the ATmega 328P contains 64 words. A word is a 16-bit long entry. Hence, 128 bytes need to be erased before any of them can be updated. Further, the program memory is divided into the so-called no read while write and a read while write section. What the differences are, we will see in a bit. Also, do note that the EEPROM, which we will discuss in the second half of this chapter, and the flash cannot be written to in parallel. In fact, the software developer must ensure that nothing interrupts the CPU while erasing and writing the data to the flash for the entire duration of the page write. No interrupt is allowed. And here comes the tricky part. How to determine which flash pages are actually free. You know that the bootloader as well as your program are somewhere in the flash. Neither should be overwritten by your data. Otherwise, the behavior of your program becomes undefined, and even a power cycle will not fix it, as the flash is non-volatile. And it will be worse if the bootloader is overwritten, since it takes more effort to reset that one. Hence, I would like to ask you to proceed with caution if you are interested in storing data to the flash while your program executes on the ATmega. If you think that this topic is too advanced, feel free to skip it and rejoin when we talk about the EEPROM in the second half of the chapter. Okay, first we have a look at the no read while write and read while write section of the flash. The bootloader is always stored in the no read while write section. How much space it occupies in that section depends on the setting of the BOOTSZ Fuse bits. As you can see, the no read while write and read while write sections are independent of the fuse setting and the size remains constant. That means if the bootloader section is small, it might happen that the section for the application reaches into the no read while write section. For the ATmega 328P, the bootloader size can be 4, 2 or 1 kilobyte or 512 byte. The smaller the bootloader section, the larger becomes the application section. The bootloader of the ATmega 328P deployed in old Arduinos had a size of 1 or 2 kilobyte. Nowadays, it shrank to 512 bytes, leaving more room for the applications. By default, the BOOTSZ fuses are set to the maximum bootloader section sizes, occupying the entire no read while write space. Okay, after getting to know the no read while write and read while write sections, why are we even discussing these? Well, the writing is very different between those two sections. Reading is not an issue. We do that daily when we execute programs on the ATmega. However, if the developer needs to write to the no read while write section to, for instance, update the bootloader, then it means that there is no read possible from the flash at all. Since the flash is the program memory and no instructions can be read anymore from the flash, the CPU is halted. If data is written to the read while write section, then the flash can be read as well, but only from the no read while write section. So, to write data to the read while write section, we have to make sure that we execute a function sitting in the no read while write section, so that we can continue to provide data to be written to the read while write section. However, the no read while write section is shared with the bootloader. That means we have to know how big the bootloader is, or in other words, what the fuse settings are. If the entire section is occupied, then we have bad luck. Except if there is an updated bootloader which is smaller in size. And in the end, we have to make sure that the software does not overwrite our program in the read while write section. First, we have to get to know if there is some space in the no read while write section left. And for that, we have to know what the BOOTSZ bits are. Fortunately, we can get this information quite conveniently. We can just read it out. An example program is attached or can be found in a VirtualBox image in the mentioned directory. As you can see, there are 4 fuses in total. Each of them has 8 bits. A peek into the datasheet reveals that we are interested in the high byte fuse only. Do note that the fuse might be different for your ATmega. Other models might not even have the high byte fuse, and I would like to refer you to the datasheet just to be sure. In my case, for some Arduinos that I have, the fuses were set to 1 kilobyte of bootloader section. In some newer Arduinos, it was set to 512 byte. So we have space in the no read while write section to place our function with a maximum size of 1 or 1.5 kilobyte. That includes a lot of functionality. My guess is that we need only a few hundred bytes. To make it easier to read the fuse bits and to interpret the results, I'm going to attach a link to a fuse calculator to the resources folder of this lecture. In it, you can just enter the value that is read by the example program and have a look at the meaning of the high fuse. If we place the function that writes to the read while write section in the flash at this address, we will be doing fine. 3800 in hexadecimal format is the first address of the bootloader section if the bootloader is maximized. Therefore, it is also the first address of the no read while write section. Okay, let's have a look at the example function directly copied from the AVR library. I'm attaching a link to it to the resources folder for more information. In line 2, the current state of the status register is stored. Its purpose is to reactivate global interrupts if they are active. Then we turn off the global interrupts so that we are not disturbed during the write process at all. Since the EEPROM and the flash cannot be written at the same time, we have to wait till a write to the EEPROM, which can take quite a bit of time, is complete. Then we erase the entire page whose address has been given to the function. In this loop, the entire page is created in a temporary buffer with the new data. However, the word size of the flash is 2 bytes and not 1 like we used to from the data memory. Thus, the word needs to be constructed by concatenating 2 bytes. That is in contrast to the address, which is byte-wise. Therefore, the loop iterator increments by 2 to access the next consecutive address of the page. Once the page is set, the page is written by the boot page write call, and we wait for the write to complete. In the second last step, the read while write section is reactivated. That is necessary, otherwise we cannot read from this section and hence cannot continue with the program which is located in the read while write section. In the last step, the status register is restored. If global interrupts were active, they are reactivated, since the bit for the global interrupts is in SRAM. If it was 0 in the beginning, then there is no change. How is this function invoked? Actually pretty easy. Make sure you give an array that is equal to the page size to the function. Here it is 128 bytes for the ATmega 328p. This array should be stored at address 100 in hexadecimal format in the flash. How do you know if the address 100 is free and not occupied by some pieces of your program. That we will see in the next session. This function needs to be located at address 3800 in hexadecimal format. To do so, we first make sure that this function is part of a section called bootloader in the resulting executable file. This is achieved by adding the bootloader section to the function prototype. How to ensure that the linker really places that section and therefore this function at the desired address. We add another parameter to the linker in the compiler call. We simply tell that the section bootloader should start at the desired address and that's it. If the executable file is analyzed, it shows that the section indeed starts at 7000 in hexadecimal format. But didn't we talk about the address of 3800 in the previous slide? Yes, we did. The issue is that every addressable entry of the flash is one word in size, that is 16-bit. However, the entire toolchain of C works on byte-wise addresses. Hence, I have to double the address 3800, which results in 7000 in hexadecimal format. Later in this chapter, it becomes more clear. For your reference, I added the entire program to the VirtualBox image in the shown directory, or it is also attached to this lecture. So far, we know how much space we have in the no read while write section in the program space, and we implemented the functionality to be placed there. There is only one question that remains. Where is space in the flash to store the data safely without overwriting anything? I will show you multiple examples how to find pages in the flash that are unoccupied, so that we can safely store data into those pages without overwriting any part of the program. Here, the organization of the flash is shown. The configuration table indicates that for the BOOTSZ setting of 11, the bootloader section starts at address 3F00. While this setting does not have any impact on the size of the no read while write and read while write sections. Their boundary is always at address 3800 in hexadecimal format. However, the application flash section size depends on that view setting. Hence, here, the last address in the flash for the application is 3F00 minus 1, which results in 3EFF. What happens if the ATmega is turned on? First, it waits till the oscillator and the power supply settle. In the second step, it checks if the fuse boot RST is set. We have not talked about that fuse yet. It determines if there is a bootloader present or not. It is not mandatory to have a bootloader. If you do not need one, the entire flash is available for your application, and the ATmega starts to execute your program immediately. Otherwise, it jumps to the address 3F00 in our case and starts executing the bootloader. The address it jumps to depends on a setting in BOOTSZ. After finishing the bootloader, the ATmega jumps to address 0 and starts executing the user program. Since we put part of our program, that is the function that is writing the data to the flash pages at address 3800 in hexadecimal format, we have a gap here between the last instruction of our program and the function boot program page. In case there is no explicit address configured where sections and their contents are supposed to be placed in the memory, the compiler toolchain takes care of that. In the end, the linker in that toolchain places the sections back to back, starting from address 0. Hence, the application grows down with the size of the user program. The pages in this gap are unused and hence available. The question is, what is the address of the last instruction here? That we have to figure out somehow. And we can even do it while executing the program, so we can determine the address dynamically. Or alternatively, we can have a look at our program and determine the last address statically. In this session we do both. We determine the last address statically and confirm it dynamically. For that, we head over to the VirtualBox image, in which I can show you a practical example. To figure out how the linker organizes the program in the flash memory, we have to know what it actually does. And for that, I'm adding the verbose option to the linker while compiling a test program. The linker is so nice to even show me the entire configuration script. And I'm looking for specific markers starting with a double underscore. Okay, I'm currently in the directory course memory flash last address in flash. And I have a little C program here that I would like to compile. And for that, I'm using the normal avr-gcc with the all warnings activated for the ATmega 328p, 16 MHz, optimized for size, and this parameter. This parameter, as indicated by the WL, is sent towards the linker, and I would like to know from the linker where it places all the instructions of the program. If we normally execute it, nothing is going to happen. But if I add the parameter verbose to the linker, then lots of text is printed on the screen. Let's have a look at it. So the linker can support these kind of architectures, and then we are very interested in the sections, where the sections are placed. And we have here, for instance, hash and the GNU version and relocation data for the text. And I'm really interested in the text section because this contains my program. Now, some of these sections within the text we already know. For instance, we have the vectors, which is our interrupt vector table. And we also came across, for instance, ctors start and ctors end. And we find these labels in our program again. So if I disassemble the program, avr object dump, disassemble, show me all headers from last address.elf, and probably there's lots of text, so I pipe it through less. then we see here, for instance, the label underscore underscore vectors, and here underscore underscore CTOS end, and here bad interrupt. And all these labels are there in the linker output. Fortunately for us, all these labels are put into the memory consecutively. It means CTOS start is followed by CTOS end and not vice versa. And here the text section ends, and everything that is within these curly brackets is put into the text section. If you remember, the text section is the section where our program is located. After the text section, a data section starts, and we see that in the data section is, for instance, the read-only data. The data section is then followed by BSS, which is part of the data section as well. In the BSS section, uninitialized data is stored. After the BSS section, we have another label, that is data load start and data load end. And then this is followed by the no init and EEPROM. That means everything below this label is not in our program anymore. This is the fuse, the log bits, signature, and so on. That means I would like to know the address of this label. So let's have a look at our disassembled program once more. If we find this label, data load end, and it turns out it is actually there in the so-called symbol table, which is a table full of symbols, and it says here that the address is DE in hexadecimal format. That means the last instruction is stored at address DE. Now please remember that these addresses are based on the C compiler. That means for the flash address I have to divide this address by 2. But let's continue. Maybe we have other options to locate this label. Fortunately, this label can be queried within the program. Let me show you what the content of last address.c is. I defined the label as an unsigned integer of 16-bit and it's an external symbol. And then I use that label, get the address of that label and store it in the variable last address. And then I just print it via UART and do that every 5 seconds. So let's see if that works and what the output is. Let me upload it and show you the content. And it prints 00DE. So that works dynamically within the program. If my program is longer, then this will change accordingly. Another option to get the size is to analyze the size of the program. And for that, we can use avr-size. We can specify the MCU, although that is not required. And the last address.elf. It says here that the program is 222 bytes. And if you check the calculator, (222) is DE in hexadecimal format. However, be careful that this number does not show the last address necessarily. The problem is that this number is without the gap. Imagine that our program starts to grow down from address 0, and then we define some functions and place them at fixed addresses in the flash, leaving gaps in between. These gaps do not contribute to the program size, hence the number and the final address will not be correct. So this number needs to be taken with a pinch of salt if the address of the last instruction is to be computed. But we have one more alternative. Remember the Intel hex format that is used to upload the program? Namely this file. Let's have a look at this. And let me show you what we had in one of the early lectures. I showed this slide. So we have the colon in the beginning, then we have the byte count that indicates how many bytes do I have in this line. In this case it is 16. The next 4 entries is the address, which is followed by the record type, which is then followed by the data, and it ends with 1 byte of checksum. Let me put this on top so we can always refer to it. If you look at our program, we see first some regular structures. This is the amount of data in this line, and this is the address. We see here that is always like C9434000, C943E, and so on. This is our interrupt vector table, which is located at the beginning of the program. And this address always increments by 16 in hexadecimal format. The last address is this one, 00D0. And if I take the last address and add the size to it, hence I have 00D0 plus 000E, which is in the end 00DE. That means the last instruction or the last entry, CF, because this is the checksum, is at address D plus the size E. So it's DE in total. Or if you want to count through, so we have the address D0 here. This is a record type. So we have here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D. That means the next free address is 00DE. And the last alternative. The linker is able to output a memory map. It's similar to the verbose mode. So instead of the flag verbose, I just added here in addition. It also accepts map and then a file name where the map should be stored. And let's say I call it last_address.map. It creates a map file whose content is very similar to the verbose output. But here you can scroll through and you have it as file. And again, we have the last entry. Should be here somewhere, and here it is. Our data load end. And that's how you figure out at what address the last instruction is stored. And with that, you know what is the address of the next page in the flash that can be used to store data. So as a summary, We know that 00DE is the last address and all the flash cells between this address till the no read while write and read while write threshold are free. What do I have to do next? I have to compute what the next free flash address is, which belongs to a new page. The problem is that if I would like to store the data at DE in hexadecimal format +1, then I have to erase the entire page first, which already contains parts of my program. I want to prevent that. Hence, I look for an address of the next page. As I mentioned earlier, the issue is that the addressing of the flash is word-wise. That means every entry at a specific address is 2 bytes in size. However, C is totally unaware of this fact and it uses byte-wise addressing. That means that the address in C are doubled when compared to the flash. In addition, there are 64 word entries for every page. Keeping these in mind, what is the next free page in the flash and what is its address in C? I'm going to interrupt the lecture here to give you time to think about it before continuing after the countdown. The address in C is 00DE in hexadecimal format. The address in the flash, therefore, is 00DE divided by 2, which is equal to 006F, also in hexadecimal format. At this address, the last instruction is stored in the flash. But we have to get to know the address of the next page. And that too, the very first entry of the next page. Therefore, we compute 6F in hexadecimal format divided by the number of words in that page. And that is 40 in hexadecimal format, which is equal to 64 in decimal. So this is 64 words in decimal. This +1 to add one more page to it, and the entire equation is multiplied with 40 in hexadecimal format. The result is 80. This is the address of the first entry of the next page in the flash after the last instruction. To make this address compatible to C, I have to multiply it with 2. Therefore, address C is equal to 80 into 2, which is 100 in hexadecimal format. And that is where this 100 comes from. But there are other options to store the data and to find free pages. For instance, instead of searching for free addresses in this direction after the program, I know this address. Hence, I can actually start using free pages going into this direction. Usually, those regions here are empty, but it depends on how large your program is. as it grows up from address 0. That means we have to get the first address of the page that is below the address 3800. That is fairly simple by subtracting the number of words in the page from the address 3800. If I do this for n pages, I just multiply the number of words in the subtrahend. For example, a software developer would like to store 1024 bytes of data at the end of the read while write region. Hence, 8 pages are required. Therefore, I subtract the number of words per page into 8 from 3800, which results in a flash address of 3600. Since C is used and C addresses by bytes, this address needs to be doubled to be used in a program. If you take this way, it is probably also a good idea to check if your data is crossing the data load end marker, which indicates the end of your program, to prevent any overwriting. Similarly, if you grow up from the first free page to store your data, it would be a good idea to check if you cross the address 7000 in hexadecimal format to prevent that your function, which is located here, is overwritten. Once you executed your program and data is stored in the flash, how do you check if it really worked, or how do you extract the data? For that, we can use avr-dude. However, instead of writing to the flash, we read the entire flash. Depending on the need of further processing, adding an I at the end of the U parameter converts the entire output directly into the Intel hex format. Let's have a look. So we are back in the last address in flash directory, and I just download the flash, and for that I'm using avr-dude with exactly the same settings like we are used to, and instead of having a W here for writing, I use an R for reading, and then give the file name I want to copy the content of the flash into. Okay, let's execute. It takes a little bit of time. It's only 57,600 baud, and 32 kilobyte need to be downloaded, so the entire flash is being downloaded. Okay, let's have a look at this. I can use the hex editor from Midnight Commander. I go to that file and press F3 for view. This is the entire flash in text format, or also in ASCII, and to see it in hex I can press F4. So here's the first address, and we see here the regular structure of the interrupt vector table, and the first free address in the flash of this program is DE. So we have here C0, and this must be then D0, so DE must be somewhere, probably this value, because the next one is E0, and that is already free. So we see here more content. We see a motor on and motor off. This is from previous projects. Or here the TWI status register. When you rewrite the flash, it's not erased, but it's erased page-wise. And if we scroll down further, you see lots of blanks here. I never had a project that used these flash cells, and at address 7000 is the boot page write program, and here the no read while write section starts. So this is from the previous upload, and if I even scroll further down, the bootloader starts at 7800, which is, just to confirm, do we have 7800 as hexadecimal divided by 2 is 3C00, which is the flash address of the location of the bootloader. To exit this on a quit, so you go one window back and again on a click, and that's it. Okay, that is all what I have about the flash. As you can see, it is possible to use the flash to store data. However, it is a lot trickier than just reading constants from the program memory, and writing depends on multiple factors, such as the size of the bootloader and your program. In addition, there is another hurdle to take, and that I have not mentioned earlier. It is possible to lock the flash and hence to prevent any overwriting of either or even both no read while write and read while write sections. Therefore, if you do not have any success in the following exercise and nothing is written to the flash, it is okay. Usually, the Arduino bootloader prevents the application from updating the flash. To lift the restrictions, we have to talk more extensively about the fuses first, that we will do a bit later in the course. The other option to store data in non-volatile memory is utilizing the EEPROM. Do not worry, operations on the EEPROM are much easier with higher chances of success and lesser chances to overwrite something unintentionally compared to what we just saw with the flash memory. Have a look at the following exercises, which combine everything that we have learned in the previous sessions. After that, I will see you in the next session about the EEPROM. Thanks for watching.